nightmares are about to come true.
The nightmare that he's talking about, of course, is actually having to remember things back from General Chem 1, and even further back occasionally to Intro Chem, the solubility rules.
Physic, jog his memory.
I'm sorry, Nigo. I didn't mean to jog him so hard.
So perhaps I won't jog your memory quite that hard, but you have seen these many times before, and they go a little something like this. All salts of sodium, potassium, ammonium are soluble in water. All nitrates, all acetates are soluble in water. Most salts of chloride, bromide, and iodide are soluble in water, except silver, mercury, and lead. Most carbonates, most phosphates, most oxalates are insoluble in water.
You keep using the word. I don't think it means what you think it means.
He probably owes you money, huh? Well, I'll ask him.
His daddy can't talk.
Look who knows so much, huh? Well, it just so happens that your friend here is only mostly dead. There's a big difference between mostly dead and all dead. Please open his mouth. Now, mostly dead is slightly alive.
And just like mostly dead is slightly alive, well, there's the mostly insoluble bit. Mostly insoluble means slightly soluble, and that's where we're going to spend our time in this topic, slightly soluble, or solubility equilibrium, with a largely unfavorable equilibrium constant. To begin with, we're going to have to write it as an equilibrium expression. That is a very slightly soluble solid dissociating in the presence of water to ions that are in solution. Keyword, in solution. The solid is not in solution. The ions are in solution. So, in terms of equilibrium, they're not in the same phase, which means it's very difficult to put them in the same expression. So, our equilibrium constant here will only include the things that are actually in solution. The equilibrium constant KSP stands for solubility product, because written as sourced from the solid towards the ions, there is no denominator. The denominator is 1. There's no reactant concentration in this expression. So for the silver chloride version, that's about 1.8 times 10 to the minus 10. A little bit on the unfavorable side, you might say. Roughly, 10 billion to 1 against. Not exactly the odds you're looking for, but that's what we're talking about, slightly soluble. Treating this as an equilibrium, it looks exactly the same as the equilibrium we've dealt with before, except there's no change in the solid side because that doesn't have a concentration. So the equilibrium expression is actually a little simpler. We only have two concentrations to deal with. In this case, they happen to be equal as long as we're starting from the solid. So we're looking at solving for x, and in this case, that's 1.34 times 10 to the minus 5 molar. This is at equilibrium, which means that it took 1.34 times 10 to the minus 5 moles of silver chloride as a solid to make this equilibrium solution, which means that's how much of the solid actually dissolved in 1 liter. But we don't usually talk about solubility in terms of moles. We generally talk about it in terms of mass. So that'll involve us taking the molar mass and converting that number of moles to grams. Usually the number is very small, so sometimes you'll see it written as milligrams, but just for simplicity's sake, we'll leave it in grams. I wrote both of them. It's a little under 2 milligrams, but 1.92 times 10 to the minus 3 grams, that's really poor solubility. You're talking about, the tip of a fingernail's worth of mass in a liter of water. That's what we mean by slightly soluble. Depending on what the K value is, we can be a little bit better or a little bit worse, but generally we're talking about these. They're exactly the same compounds that we talked about in General Chemistry 1 and called them insoluble. So at that point, though, we're actually at equilibrium, which means Q is equal to K, which also means that's a saturation point. No more than that will dissolve unless you change the temperature, and that's beyond the scope of this type of question because that also changes the equilibrium constant. What if we didn't have that much silver? What if we didn't have that much silver chloride there to begin with? What if we only had a fraction of that amount? It means that we never get to equilibrium. It means Q will always be less than K, and therefore the solution that comes from that would be unsaturated, meaning it would be capable of taking in more if there were more around to take in. What happens if we had more than that amount of solid? Now, what I've written here is Q is still equal to K, but does that make sense? In actual fact, yes it does. Because there can't be any going beyond saturation, that means that in a case where there was more than that amount of solid, there would just be some of it left on the bottom of the flask. It won't change the concentrations in the flask, in the solution, because it won't go into solution beyond that 1.92 milligrams. The rest of it will be sitting on the bottom doing nothing. So the second type of permutation of this type of question is, what if they didn't come from a common source? And this is the type of thing that you deal with in the lab. You dealt with it in intro chem when you did the cations. You dealt with it again in general chem 2 when you do the more extensive cations experiment. You're basically causing these reactions to happen to remove a solid, but you want to make sure you get all of it, and generally you're adding something to cause precipitation. So I would have a soluble version, in this case, of the silver ion, maybe from silver nitrate, that's a very common one, and a soluble version of the chloride ion, which could be anything other than chloride from silver, mercury, or lead. And when I put them together, I'm actually going to get a solid forming the instant that I get to K. Now, as I'm going along, at any instant, I can look at those concentrations and say that's Q. When Q becomes equal to K, the solution is saturated in silver chloride, silver ion and chloride ion. So as soon as I go one molecule beyond that, I'm going to see a solid form. And that's what precipitation reactions really are, is you've driven it past equilibrium to the point where now it's shifting away towards reactants to escape the concentrations being too high on the product side of the way the solubility equilibrium is written. So here's what that would look like. We have the equation. These are the sources that are commonly used. The nitrate for most metals, they all dissolve. The potassium or ammonium salts for whatever else. And during that you form a solid. Don't think that this is a different equilibrium. It is not. Remember, when you did these as precipitation reactions in intro chemistry or in general chem 1, you would have written this out as a net ionic equation. The potassium and the nitrate would have ended up as spectators. They get canceled out. Well, that's exactly what we're looking at here. Except, and this is a big one, we don't write it in that direction. Solubility equilibrium expressions always begin from the solid. Regardless of how they end up in the reaction, the equilibrium constants are calculated beginning from the solid. So while this reaction does produce the solid, we're going to treat it as if it were an equilibrium with the solid on the reactant side, despite how it looks in the reaction itself. So if I were to say that I gave you half molar potassium chloride, so that's my chloride ion concentration, and ask you how much, or what is the concentration of silver nitrate when this begins to form, so at what silver ion concentration will I actually get to the point where Q equals to K, here's what that looks like. I plug that in directly. I don't have to do algebra here at all. I just put in the chloride concentration, put in KSP, solve for the silver ion concentration. You'll notice it's actually really small. This is a lot less silver ion than we had in the original solution when I began from the solid. That's because I have so much excess chloride ion, and their relationship in solution at equilibrium can only be KSP. So if one of them blows the numbers out, well then the other one has to be much, much smaller at the equilibrium point, which means precipitation will happen much more rapidly. And that's part of why we do that qualitatively in General 1 and in Intro, is just so you see the solid happen, and then you can filter it or whatever. So the next variation on a theme is what happens if it's not quite so straightforward. And the first one, and I will beat you up for this on exam day, and I have done it in Intro Chem and General Chem 1, and I'll continue to do it forever, you have to deal with a balanced equation. If you don't do that, you have a big problem on your hands. So if you didn't balance this, you're going to have some expression that makes no sense. You're going to get numbers that make no sense if you don't balance the equation first. You need that 2 present because that is an exponent in your equilibrium constant expression. You leave that out, you get something that makes no sense. So the problem with that, though, is the 2 gets in the way later on. Not in this version of the question, which is to solve the concentrations at equilibrium starting from the solid, but in the other version of the question, which we'll get to in a few minutes. So at equilibrium, we're talking about a change of X for calcium and twice that much for fluoride. So we're looking at X and 2X, which means if I put those into the KSP expression, I'm looking at squaring that 2X and getting 4X squared times X equals 4X cubed, which is my KSP expression. Nowhere will I see more bizarre mathematical tricks than right here. I have seen the strangest things mathematically. I've seen people take that 2 and ignore it, pull it out without squaring it, leave it out altogether if not a balanced equation. It hurts my head sometimes. So just be really careful with that so you know it's there, and once it's there, you have to treat it mathematically correctly, which means 2x times 2x is 4x squared. And that times x is 4x cubed, which is the point here. So we can solve just like we did before for x. That gives us our concentration. In this case, though, x doesn't represent both of them. One of them is represented by x. The other is represented by 2x. You cannot forget that because otherwise you have a concentration for the fluoride ion that is not correct and does not give you an equilibrium value when you mix those amounts. So you have to remember to put that back into place. All right, so what that means is that we have, since the calcium ion and the original solid are stoichiometrically related 1-to-1, then we can say that because we have 2.15 times 10 to the minus 4 moles per liter of calcium ion, that's how many moles of calcium fluoride as a solid had to dissolve in 1 liter to make that equilibrium solution. So we can work out from that and the molar mass of calcium fluoride that we need a little bit less than 17 milligrams of calcium fluoride to reach equilibrium. So a little bit better solubility than what we saw for silver chloride, but still really bad. Again, slightly soluble, the emphasis there on the word slight. This is not a lot of solubility here, but it's also not zero. So we have to take that into account. All right, the trickier version of this question happens when we're dealing with 2 different sources. And what I mean by that is if I had a solution of calcium something or other like calcium nitrate that dissolves well, and I add a fluoride source to it, at what point do I get to equilibrium? Here's where we start to have some big problems. In the KSP expression, we have a concentration for calcium, we have a concentration for fluoride, and because of the relationship in the balanced equation, we have an exponent on the fluoride, in this case a 2. That is all we have. So if I put in together solutions from different sources that give me concentrations directly, I do not change them. That 2 in front of the fluoride ion is only doubling things if it came from the same source as the 1 in front of the calcium. In a problem like this, it doesn't, so you do not use the 2. Here's what that looks like. If I started with a solution of calcium at 0.5 molar, very similar to the example we did earlier, at what point do I have enough of at what point in the fluoride concentration do I see a solid? Again, this is where we're going to get to Q equals K, so I'm looking for the fluoride concentration directly from this expression. That's exactly what I'm going to solve it for. I'm going to put the calcium concentration in place, solve for the fluoride concentration by taking the square root once I'm done. Do not double it. There is no 2x if there is no x. Those 2 are related 2-to-1 only if they came from the same source. In a question like this, they did not. And it'll be stated that way. Calcium nitrate, sodium fluoride. In this case, I left those pieces out. But you can look at the example earlier to see what I'm talking about. There'll be the sources for the calcium will be not the same as the source for the fluoride, which means I don't have to deal with x and 2x. I just have to deal with the KSP expression alone. I still have the square that's always there, the exponent on the fluoride ion, if it came from something that is formula-wise F2, but I don't have the 2 within the brackets because that is an algebra trick rather than a concentration one. So it means that at equilibrium, we have a very, very tiny amount of moles per liter of the fluoride ion, since the calcium concentration was very, very high.
Bye-bye, boys.
Have fun storming the castle.
Think it'll work?
It would take a miracle. Bye-bye.